Hi, my name is Weber, and my teammates are Solomon and Alexander, and together we are Group 7. Today we are presenting parallelization of computationally expensive image processing algorithm. So the content we will be covering in this video is an overview of a basic image processing application, algorithms that are used in our image processing application, and out of countless image operations, a specific image operation called Delaunay triangulation, and how did we achieve parallelization in Delaunay triangulation, the analysis and implementation part, and then benchmarking and result of the intended parallelization, and then finally future considerations. So this is how a basic image processing system works. It's just not about spatial resolution of the image. It's just not about the adjustment of coordinates of the image. It's much more extensive than that. We have image enhancement, acquisition, restoration, pattern recognition, encoding, compression, and much more. So out of these countless image operations, one of them is Delaunay triangulation. On the screen, you can see we have a set of points. And if we connect those points, we have a set of triangles. And each triangle has a circumcircle drawn to it. Every triangle has a circumcircle that encloses all of its edges and vertices. And if we observe carefully, no point in this plane is inside in the circumcircle of any triangle. Every point is on the circumference of the circumcircle. So this is a very basic definition of Delaunay triangulation. Delaunay triangulation is for a given set P of discrete point in a plane such that no point in P is inside the circumcircle of any triangle in the plane. Now, how do we determine Delaunay triangulation? How do we validate Delaunay triangulation? A very straightforward approach to it can be seen on the screen. We have 3 points, A, B, C. We connect them, we get a triangle. And then we draw the circumcircle of the triangle. If any point D is inside the circumcircle of the triangle made by points A, B, C, then determinant of this 4 cross 4 matrix will be greater than 0. So what I mean to say, if D is inside the circumcircle of this triangle, then the determinant will be greater than 0. In the determinant of this 4 cross 4 matrix, we have AX, BX, CX, and DX that represent the X component of each point, X coordinate of each point. Similarly, AY, BY, CY, DY represent the Y coordinate of respective points. And AX square plus AY square is the magnitude of A from the origin. Similarly, BX square plus BY square, the square and the summation represent the magnitude of respective point from the origin. And in the final column, the fourth column, we have all the ones. So if the determinant of this 4 cross 4 matrix is greater than 0, then point D lies inside this circumcircle. One of the most prominent methods to calculate, to determine, to generate Delaunay triangulation is Boyer-Watson algorithm. So a small illustration can be seen on the screen. We insert one point at a time from the desired set of points, and then check if the new point is inside the circumcircle of any triangle. If it is inside the circumcircle of any triangle, then we delete those bad triangles, leaving a polygon void in the whole triangulation, in the whole mesh. And then finally, we retriangulate that star-shaped polygon void by inserting a new point. So the flow chart, this is a flow chart of our image processing application. We have an input image, then we apply Gaussian filter to it to have a blurred image. Then the blurred image is converted into a grayscale image. Grayscale image, then we apply Sobel operator on the grayscale image, and Sobel operator is applied for edge detection. And then a threshold filter is applied to reduce all the noises and to generate a set of points. Now we have set of points, then we apply Burr-Watson algorithm to have the Delaunay triangulation of that image. And then finally, we have the processed output image. So we found a GitHub project that converts a real life image into its respective Delaunay triangulation. So this is an example, the input image and its Delaunay triangulation. The next part, the parallelization analysis and implementation, will be explained by Solomon.
This is Solomon. I'll be talking about the analysis and parallel implementation in this section. The first step in the process of parallelizing this project is to determine what needs to be parallelized. For this, we look at the timing analysis of the sequential implementation of the various algorithms used to create the final output image. In the sequential version of the program, we consider our standard test image and specify 25,000 points. We can see that it takes 250 milliseconds to load the image, and the triangulation time was approximately around 13 seconds, and the application runtime was around 17 seconds. So now we look at the sequential execution with different number of edge points. So here we have 25,000 edge points. You can see the triangulation time was around 13 seconds. Here we have 50,000 edge points, and it was around 65 seconds. Similarly, 75 was nearly 180 seconds, and 100,000 points was around 288 seconds. So looking at all the other data, it's nearly constant, whereas your triangulation time increases exponentially with the number of points. Therefore, our focus of parallelization will mainly be on the triangulation algorithm. In order to do parallelization, we need to look at the sequential triangulation algorithm, which is the Boyer-Watson algorithm. So basically, the algorithm takes an array list of edge points and the size of your input image. So then we need to create a super triangle. A super triangle is a triangle basically that whose circumcenter encompasses the whole image. So basically, if you divide the picture by the diagonal, you get two triangles, and the circumcircles would be coincide, and the entire image would be within that. The next step in our algorithm is to take a point and sort all the triangles to either good triangles or bad triangles based on if this point lies within the circumcircle of the triangles. So here, that's our point, and if both these triangles circumcircle is contained by this point, so basically both of these triangles are bad triangles in this example. Now we look at creating new triangles. To do that, we take a list of bad triangles and find any bad triangle that shares edges with other bad triangles. So for example, we have these two bad triangles and this is a shared edge. So we basically remove the shared edge, and all the other edges are added to a polygon. So all these edges are added to a polygon. And then we have the point which we are considering. And then we join that point to all the edges of the polygons, creating new triangles. So therefore, we generate 4 new triangles in this example. So basically that if we give this as our input image, after the first iteration, we get this, which is similar to what I had drawn previously. And then we use the newly created triangles, and that would be the output of the second iteration. So in summary, this is the entire code which we had looked at previously. We iterate over the edge points, and we sort the different triangles to good and bad triangles. And then we compare with the other bad triangles to find shared edges and remove the shared edges to create the edges of the polygon. And we join it to the point to create new triangles. And this whole process repeats. So now in the dependency analysis, in order to parallelize this, we can see that since we are writing over here and reading over here, there exists an inter-iterational dependency. So therefore, we cannot parallelize over here, but we can parallelize where we are sorting the triangles. So we have implemented different parallelized versions. So first we implemented fully parallel. We knew that the performance was going to be bad, but once we implemented it, it was really bad, and we couldn't even finish the execution. We will be looking at static and dynamic scheduling. Here we look at the parallel version of our algorithm implemented with static block scheduling. In static block scheduling, we divide the array list of triangles equally among worker threads. We do parallel computation once the number of triangles is more than 50,000 due to the overhead being greater than sequential sorting below that. Once all the triangles are sorted, we create polygon and new triangles, which is then used iteratively by the next edge point to generate new triangles. Here we look at the implementation. Each thread sorts the triangle from its private list and adds to its private lists. Once finally the thread is done, it gets added to the central list and shared among different threads. In dynamic scheduling, we use a central concurrent list which gets shared among different threads. Each thread retrieves a triangle from the queue and sorts it. Once the queue is empty, it gets added to the central list. Alexander will discuss the results of benchmarking.
Hi, my name is Alexander, and I'll be talking about the results of parallelizing our image processing algorithm and our future considerations after that. To measure our results, we first looked at the results of our sequential implementation. Solomon explained how we ran this and the different times we got out in his time analysis section. What we did was we gave it an input image with a size of 3072 times 4608 pixels. And then we calculated the triangulation times for 25,000 points, 50,000, 75, and 100,000 points. We got 4 different triangulation times out from this. For 25,000 points, it was 13.6 seconds. For 50,000, it was 65.5 seconds. For 75,000, it was 180.5 seconds. And for 100,000, it was 288.5 seconds. These times worked as our benchmark, and we used that to calculate the speed up of our parallel implementation for the different number of points. Our parallel implementation was first executed with a static scheduling policy on the same 4 workloads, and we did this using 2, 3, and 4 cores. After that, we executed our parallel implementation with a dynamic scheduling policy, and then we tried running it on a different machine. The results of running our parallel implementation with 2 cores and a static scheduling algorithm can be seen in this graph. We calculated the speed up as the sequential triangulation time over the parallel triangulation time. It's worth noting that the only reason there's a comma here is because of my language formatting. The speed up is in fact 1.026, 1.108, 1.223, and 1.264. It can be seen that the speed up is steadily increasing and at different rates depending on the size of the workload. For static scheduling with 3 cores, we got a similar graph. Again, the speed of is slowly increasing. We see that it's increasing significantly more when we reach 75,000 points. We reach a speed of 1.4. Then it drops as we reach 100,000 points and get a speed of 1.384. This is with 3 cores. It's worth noting that the device we've been testing these on has 4 physical cores. And for that reason, the final test we ran was static scheduling with 4 cores. We see similar results. Speed up is steadily rising, and it reaches almost 1.45 as we reach 75,000 points. But then again, it drops this time more significantly than for 3 cores as we reach 100,000. So we see a rise until 75,000 and a significant drop afterwards. We tried running the program, the parallel program as well, using a dynamic scheduling policy, and the results can be seen here. When we used the dynamic scheduling policy, we discovered that because our program is using a centralized shared queue, this becomes a bottleneck for the dynamic scheduling policy. All the workers have to wait for the queue. Thus, the runtimes become much worse than sequential. We saw that for 25,000 points, it took 95.8 seconds, and for 50,000 points, it took 361.7 seconds. So the speed up is there's no speed up, and the triangulation time increases almost exponentially as we increase the workload. So we decided not to pursue this any further. When we compare the speed up for the static scheduling policy, we see that for 2, 3, and we see that with 2 workers, it consistently performs the worst. The first part here is probably most likely due to runtime deviations, as all 3 implementations works essentially sequential below 30,000 points. But when we reach above 30,000 points, that's when we start to see the difference, and we see that at 3 and 4 workers is significantly faster than 2 workers, and we see that at 100,000 points, 3 workers is the fastest one. Our theory is that the reason for this is that the device only has 4 cores, which means that the 4th core is always going to be used for some small things in the background, like running the operation system. And for that reason, it's not able to fully utilize the 4th core. So the reason we see it performing slower than the 3rd core is actually because the other workers are waiting for the 4th core to finish. To confirm this, we also did a comparative result on a different machine. This time we only tested with 60,000 and 100,000 points to see if we had a decrease in speed up as we reached that mark above 75,000 points, as we saw for machine 1. We tried running it with 1 core as well, and we saw that it performed worse than sequential. Apart from that, we saw the same results and further confirmed our theory that it's not able to fully utilize all 4 cores. Finally, we have a graph comparing the triangulation time of the static scheduling policy versus the triangulation time of the sequential implementation. From this, we can see that the sequential is clearly the slowest for all cases except where they're all essentially running sequentially, which is 25,000 points. Apart from that, it's the slowest one for each of them. Then parallel with 3 and 4 workers performs best from that point on, and we see that parallel with 3 workers performs best at 100,000. The difference in time here is roughly 80 seconds. The difference in time here is 50 to 55 seconds. For future work, we would like the opportunity to test the program on a machine with more cores, if that's possible. This would help us confirm our theory that it's not fully utilizing the 4th core. And we could also try and see how much speed up we can get as we increase the number of cores. Apart from that, we would also like to try testing it with a larger workload. We'd like to see how far we can scale it, how big the workload can get before we don't see any more speed up. Yeah, and of course, how much can we handle before it starts to take too long? Further, we would also like to create a GUI. The GUI should be able to take an input image and a number of workers, and maybe we should be able to specify a specific application runtime at which it stops creating triangles, just outputs an image with the number of triangles it created within the specified runtime. Finally, we'd like to compare our output images for quality and consistency. We don't really have a method right now, but we'd like a method to compare them between our sequential and parallel implementation to see if there's any differences. And finally, if we have more time, we might look into different image algorithms. And this concludes our presentation. We've been Project Group 7. Thank you very much for listening.